Hi everyone, welcome to another micro lesson in microblasting. I'm Colin.
And I'm Pat.
Have you ever wondered what the right setting on your regulator is, or what role blast pressure plays on your microblasting process? We'll review these important points in the episode today.
To start it off, there are three characteristics that will impact the results you get from microblasting: the abrasive type and size, the amount of abrasive flowing through your system, and the particle speed or velocity.
A common question we get asked from customers setting up a new application is, what's the right setting on my pressure gauge? This can be a difficult question to answer because so many variables impact the blasting process. But by having a good understanding of how particle velocity impacts our process, a good starting point can be achieved. Blast pressure is directly related to abrasive velocity. While not linear, high pressures result in faster speeds. The relationship is affected by particle size, mass, and shape.
For many applications, there is a lower limit to the blast pressure setting. To cut through a ductile layer, the abrasive must be traveling at a high enough velocity to cut through the fibers without bouncing off.
If there's a brittle layer below, there may also be an upper limit to blast pressure. If the abrasive particles are traveling too fast, they can damage that brittle layer. In some cases, particle velocity can also be used to separate individual layers of an assembly. Particle velocity is also important when using microblasting to create a specific surface finish, whether it's to promote osseointegration or improve a mechanical bond. The velocity of the particle determines the surface roughness. Higher pressure results in deeper pits. By controlling both particle size and velocity, we are able to engineer specific surfaces. The result is a feature with a controlled diameter and depth of each pit.
When deburring stainless or titanium with glass bead, higher pressure will make the process run faster. In these cases, however, there are a few things to consider.
Higher pressure makes the process more operator dependent. It takes a skilled operator to find the right balance without overblasting.
An increase in blast pressure does not provide an equal increase in particle velocity. Above 120 psi, there is only a slight increase in particle speed. In most cases, there's no benefit to blasting above this point.
By combining high velocities with an aggressive abrasive media, you will increase the wear inside your machine. The abrasive wears out anything it touches. So combining silicon carbide with high blast pressures will wear out your machine faster than the benefit to your application. As abrasive exits the nozzle, it continues to accelerate. In fixtured applications, pressure can be used to normalize velocity over varying nozzle distances.
An interesting thing happens with soft abrasives like sodium bicarbonate. At high pressure, the particles detonate on impact with the surface if the material does not etch away quickly enough. This makes the process ineffective.
An important note is that increasing blast pressure will not increase abrasive flow. If you need a richer abrasive stream, change the orifice in the abrasive tank. So, over time, we've found the best starting point for most applications is between 50 and 80 psi. This gives the best balance between precision and control. It also leaves plenty of room, both higher and lower, to further optimize your blasting process for your specific application. On our website, you can find case studies which detail specific applications. In those studies, we go into greater depth on how specific abrasives and material interact.
If you have more questions or would like to send us sample parts, contact our technical support team.